Have you ever looked at a circuit diagram and wondered why some sources are circles while others are diamonds? That little diamond shape is the secret to understanding how your smartphone, your laptop, and almost every modern electronic gadget actually works. Welcome back, everyone. Today, we are pulling back the curtain on the powerhouse of electronic modeling: dependent sources in electrical circuits. If you look at this first circuit on your screen, you'll see a mix of components that might look a bit intimidating at first. On the far left, we have a standard 10 milliamp independent current source. But then, look over at the right side where you see that diamond symbol labeled 4, I sub O. This is a dependent source, and its entire behavior is tied to the current I sub O that is flowing through the 3 kilo ohm resistor in the middle of the circuit. If that current changes, the source changes. So, let's break down the basics. What is a source? Simply put, a source is what supplies power to your circuit. There are two main types you need to know: independent and dependent, which is also frequently called a controlled source. While an independent source just does its own thing, a dependent source is a source whose value depends entirely on a different voltage or current somewhere else in the circuit. It literally cannot work on its own because it is being controlled by another variable. You can always spot them in a schematic because they are drawn as a diamond shape. These sources come in two primary categories: dependent voltage sources and dependent current sources. To get even more specific for our analysis, there are actually 4 distinct types based on what is doing the controlling and what the output is. First, we have the voltage-controlled voltage source, or VCVS. Here, the output is a voltage that is scaled based on another voltage in the circuit. The multiplier used here is known as the voltage gain. Next is the voltage-controlled current source, or VCCS. This source puts out a current that is controlled by a voltage. The relationship between that voltage and current is defined by transconductance, which we measure in a unit called Siemens. Then we have the current-driven versions. The current-controlled voltage source, or CCVS, outputs a voltage based on a controlling current. The scaling factor here is called transresistance, measured in ohms. Finally, there is the current-controlled current source, or CCCS. This is where one current controls another current, and the multiplier is simply called the current gain. Now, why does this matter? Because dependent sources are the only way we can accurately model real-world devices like transistors and operational amplifiers. Without them, we wouldn't be able to properly analyze or design the amplifiers that power our world. Let's walk through a step-by-step example to see how the math actually works. We have a circuit with a 6-volt independent source, a 4 kilo ohm resistor, a dependent voltage source labeled 2V sub A, and an 8 kilo ohm resistor. Our first goal is to find the value of V sub A. Using Ohm's law, we can express V sub A as the current I multiplied by the 4 kilo ohm resistance, giving us 4,000 times I. Next, we apply Kirchhoff's voltage law, or KVL, in a clockwise direction around the loop. Starting from the 6-volt source, our equation looks like this. When we substitute our expression for V sub A into this equation, it simplifies everything into a single variable. After simplifying the terms, we are left with -6 plus 4,000 I equals 0. Moving things around, we find that the current I is exactly 1.5 milliamps. To finish it off, we plug that current back into our original Ohm's law equation to find that the voltage V sub A is 6 volts. And that is how you solve a circuit with dependent sources. It's all about finding that relationship between the controlling variable and the source itself.